Assalamualaikum everyone, this is the power transmission course. In the last lecture we were talking about the string efficiency of the string insulators, and the string efficiency, it is actually the measure of the voltage distribution among the different discs of the string insulators. And ideally the voltage should be uniformly distributed, which means that the voltage across all the discs should be same, and in that case the string efficiency would be maximum, which is equal to 100%. After that we derive the mathematical expression for the voltages across different discs, and the self capacitance, it was denoted by capital C, and the shunt capacitance, they were denoted by the capital C1. Then we applied the KCL at node A and node B and node C, and from there we calculated the voltage values. Then in order to improve the string efficiency, we defined few methods. The first one was the longer cross arm. We have to increase the length of the cross arm, which is actually the support for the insulator and is attached to the tower. So if you will increase the cross arm length, then the value of K will become smaller, because the capacitance C1, which is the shunt capacitance, the value will be reduced and the value of K will be reduced. So if the value of K is reducing, the string efficiency will be increasing, which means the voltage distribution along all these insulator will be becoming more uniform. And in practice the maximum value of K is approximately equal to 0.1. So this was the first method. The second method is that we have to use the graded insulator, and the grading was dependent on the capacitance value. So the insulator that is closest to the conductor is actually having the largest capacitance. So if the capacitance is larger, the capacitive reactance will be smaller. So if the capacitive reactance will be smaller, the voltage will be smaller across the insulator that is closest to the conductor. The limitation of this process was that the discs that we have to use should have different sizes, because the capacitance should be different, so the sizes of the insulator should be different, which is not feasible. So in practice what we do, we actually use a larger unit or larger insulator closer to the conductor. So if it is larger, the capacitive reactance will be smaller and the voltage across that particular insulator will be smaller, and all the remaining insulators will have the standard size discs. So this was the second method of improving the string efficiency. The last one was that we have to use a guard ring. It is actually a metal ring which is electrically connected to the conductor, and it surrounds the bottom insulators. For example, in this case it is surrounding the two bottom insulators, and it actually introduces a capacitance between the conductor, which is the conductor, this one, and the guard ring is attached to the conductor. So it introduces the capacitance between the conductor and the metal fittings of the insulators. So what it actually does, it makes the shunt capacitance current, which is for example in this case small I2, this is the shunt capacitance current, make it equal to the line capacitance current, which is I2 dash. So if these two currents are equal, then the current I, capital I, which is passing through the self capacitances, that will be approximately same, and if it is same, then the voltage distribution along all the discs will be same. So what we have done, we have increased the string efficiency of the string insulator, and voltage is uniformly distributed. So this was the last method of improving the string efficiency. So now we are going to solve few examples. So in the first example we are given a string insulator in which we have three discs. They are represented by three self capacitances. Then we have three shunt capacitances. We have a conductor at the bottom of the string insulator, and then we have a tower which is grounded. So now what we have to do, from the question we know that it is a three-phase system, and if the voltage across the line unit is 17.5 kilovolt, so the line unit is the one which is closest to the conductor. So the one that we are talking about is this one, and the voltage across the line unit is V3. So V3 is equal to 17.5 kilovolt. So now what we have to find, we have to find the line to neutral voltage. So this is the voltage that is between the conductor and ground, right? So this voltage is actually the summation of all the three voltages. It is V1 plus V2 plus V3 it is equal to V. So we have to find this V, which is line to neutral voltage. So now what we have to assume, there is a shunt capacitance which is this one, and its value is actually 1/8 times the self capacitance. So from the formula we know that C shunt is actually equal to K times C self. So if C shunt is 1/8 times the value of self capacitance, then the value of K is actually equal to 1/8, right? So these are the things that are already given, and also we have to find the string efficiency. So we have to calculate two things. The first one is string efficiency and the second one is line to neutral voltage. So we will start from applying KCL at node A and node B. So I will be starting from KCL at node A. For KCL it will be I2 is equal to capital I1 plus small I1, right? So the capital I2 current is moving towards the node A, and current capital I1 and small I1, they are moving away from the node A. So this is the KCL equation at node A. Now if I have to find the current I2, it will be the voltage across that particular capacitance into capacitive reactance. So the voltage is V2 into omega C. And for I1 the voltage is V1 and capacitance is C, then it is again V1 omega C. Similarly for small I1, it is the voltage again at this point A is V1. From this point to this grounded tower it is V1, so it will be V1 K omega C, right? I am not using the value of K right now, so just for the simplified equations I am just using the value K omega C. And after I have calculated the equations for the voltages in terms of K and capacitance, then I will use the value of K. So after solving this equation I will get omega C V2, it is equal to omega C V1 into 1 plus K. And cancelling out the omega C, V2 is equal to V1 into 1 plus K. So this is your equation A. Now for KCL at node B, again there is one current that is moving towards node B, and two currents I2 and small I2, they are moving away from the node B. So the KCL equation will be I3 is equal to I2 plus small I2. For I3 the voltage is V3 and the capacitive reactance is 1/omega C, so it is omega C V3. For I2 the voltage is V2, self capacitance is C, so it is omega C V2. Now for small I2, the voltage from this point to ground, it is actually equal to point V to this ground, right? So these two values, this one for example this is VA and this is VB, they are equal. So this VB is actually the summation of V1 and V2, so I will write it down as K omega C into V1 plus V2. And now after solving this one, omega C V3 is equal to omega C, I will take omega C common and it will become omega V2 plus K V1 plus V2. Omega C will cancel out and it is V3 is equal to V2 plus K V1 plus V2. This is your equation B. Now we know that value of K is equal to 1.8, and I will be using this value in both the equation A and equation B, and after putting the value of K, the equation A will become V2 is equal to V1 into 1 plus 1/8 and V2 is equal to 1.125 V1. Similarly for the second equation B, V3 is equal to 1.125 125 V1. So this is the value of V2, which is this equation, plus K value is 1 over 8 into V1 value is V1, and for V2 it is 1.125 V1. So the final V3 value will be 1.39 V1. Right? Now from the question we know that the voltage across the line unit, it is actually 17.5 kilovolt, right? So the voltage V3 is 17.5 kilovolt. So if I will use the value of V3 in equation, for example A, the value of V3 will be 17.5 kilovolt, and by putting this value into equation A, V1 will be equal to 17.5 over 1.39, and it is equal to 12.59 kilovolt. And by using this value in the equation of V2, V2 will be equal to V1 into 1.125, and V2 is equal to 12.59 kilovolt into 1.125, and the V2 value is 14.16 kilovolt. So what we have done, we have calculated the voltages, all the three voltages across the discs of the string insulator V1, V2 and V3. So the first portion of the question was we have to find the line to neutral voltage, and line to neutral voltage was V is equal to V1 plus V2 plus V3, and by putting the values it is 12.59 plus 14.16 plus 17.5 kilovolt, and V line to neutral is 44.25 kilovolt. So this is the first part of your question. The second part is we have to calculate the string efficiency, and the formula is voltage across the string so which is equal to V line to neutral divided by total number of insulating discs into V3, the voltage across the disc which is closest to the conductor. So it is 44.25 into 100 over 3 into 17.5. So the efficiency value is 84.28%. So this is the second part of your question. So in the question we were asked to find the line to neutral voltage, which is the voltage between the grounded tower and the conductor, and it is the summation of all the three voltages V1, V2 and V3. And the second portion was we have to find the string efficiency, which is actually the ratio of voltage across the string, which is V line to neutral, divided by the total number of insulating discs multiplied by the voltage across the insulator which is closest to the conductor. So the efficiency value came out to be 84.28%. So this was the first example. Now moving on to towards the second example. In the question we are given with the string insulator. The self capacitance of each unit is a string of 3 suspension insulator is C. So the self capacitance is this one. Then we have shunt capacitance which is equal to 0.15 C, and now we have a guard ring. So we have line capacitance as well, which is 0.1 C, and now what we have to calculate, we have to find the voltage across each insulator as a percentage of line voltage to earth, right? Line voltage to earth, V line, it is actually equal to V, which is the summation of all the voltages V1, V2 and V3. So what we have to do, we have to find the voltage across each insulator. We have to find V1, V2 and V3 as a percentage value of the line voltage, right? And the second thing is we have to find the string efficiency. So these are the two things that we have to find out. So again, we will start by applying the KCL at these two nodes. So starting from KCL at node A. So now we have four currents, I1 capital and small I1, they are moving away from the node. Then capital I2 and small I1 dash, that is moving towards the node A. So the equation will become I2 plus I1 dash is equal to I1 plus small I1. And after using the formulas for the currents, for I2 the voltage is V2 omega C plus I1 dash, the voltage is from this point till this point, right? Because this is the voltage, this point is actually connected to the conductor. So the voltage from this point to this point, for example this is your VA, it is actually equal to a voltage from point A till the conductor, this is VB. So this VA is actually equal to voltage VB, which is from point A to point C. So VB, it is actually the summation of V2 and V3. So for I1 dash, it is V2 plus V3, the voltage value, and then the capacitance value is 0.1 omega C. Now the other side of equality, that will be I1. So I1, the voltage is V1, so it is V1 omega C plus, for the shunt capacitance the voltage is again V1, so it is 0.15 omega C V1. Now after solving, it will become omega C into V2 plus 0.1 into V2 plus V3 is equal to omega C V1 plus 0.15 V1. So V2 into 1 plus 0.1 plus 0.1 V3 1.15 V1. So V3 value will be 1.15 over 0.1 into V1 minus 1.1 over 0.1 into V2. And after solving, it will become 11.5 V1 minus 11 V2. So this is your equation A. Now we will apply KCL at node B. So this is your node B. So for KCL at node B, we have small I2 plus capital I2 is equal to I2 dash plus capital I3. Now for small I2, again the voltage V1, it is actually the same voltage that is between these 2 points, which is V2. So this V1 is actually equal to V2. So it is the summation of V1 and V2. So it will become 0.15 omega C into V1 plus V2 plus omega C V2. So V2 is the voltage across this capacitance, and for I2 dash, this is I2 dash, so this is the same voltage as V3. So I2 dash, it is V3 omega C 0.1 plus C omega V3. So then after solving, it will be omega C into 0.15 V1 plus V2 plus V2 0.1 V3 plus V3 omega C will cancel out, and it will become 0.15 V1 plus 0.15 plus 1 into V2 1.1 V3, and the value of V3 will be 0.15 over 1.1 V1 plus 1.15 over 1.1 into V2. So the final equation will be V3 is equal to 0.136 V1 plus 1.045 V2. So this is your equation B. So now we will equate equation A and equation B, and we will find out the values for V2 and V1. So now what we are going to do, we are equating equation A and B. So it will be 11.5 V1 minus 11 V2. So this is equation A, that will be equal to 0.136 V1 plus 1.045 V2. And after solving, 11.5 minus 0.136 V1, it is equal to 11 plus 1.045 into V2, and the final value of V2 will be 0.94 V1. So this is the value of voltage V2 in terms of V1. Now if I will put this value in equation A, then V3 will become 11.5 V1 minus 11 V2. Replace this V2 value with equation 1. So that will become 11.5 V1 minus 11 into 0.94 V1. And this is 11.5 V1 minus 10.378. And final value of V3 will be 1.122 V1. So now we have the voltage value V2 and V3 in terms of V1. For the value of line to neutral voltage, which was the first thing that we have to find, and it is also known as voltage across the string. So it is V, it is equal to V1 plus V2 plus V3, and the values are V1 plus V2 in terms of V1 is 0.94 V1 plus 1.122 V1. So we have calculated these two in equation 1 and equation 2. So the value of V is V1 into 1 plus 0.94 plus 1.122, 3.062 V1. So this is your voltage across the string in terms of V1. And from this equation we can write V1 is equal to V over 3.062, right? So now we have the values of V2 and V3 in terms of V1. So from here we can calculate the values of V2 and V3 in terms of voltage across the string. So V2 is equal to 0.94 V1. So it is 0.94 into V over 3.062. So this will be equal to 0.326 V volts. Similarly for V3, it is 1.122 over 3.062 volts, and this will be 0.364 V volts. So now what we have voltages V2, V3 and V1 in terms of voltage across the string. And from the question we know that we have to find the voltage across each insulator, which is V1, V2 and V3 as a percentage of the line voltage to earth, right? So now what we have to do, we just have to find the percentage values, right? So for the voltage across each unit, expressed as a percentage of voltage V, which is line to neutral voltage, Now for the top unit, the voltage is V1, right? So V1 over total voltage into 100, and we know that V1 is equal to 0.326 V. So this will become 0.326 V over V into 100. So these V will cancel out, and for top unit it will be 32.6%. Similarly for the second from top, or the middle one, we have V2 over V into 100. Again V2 is equal to 0.307 V volts, so it will become 30.7%. And for the last one, which is closest to the conductor, we have V3 over V into 100. V3 is equal to 0.364 V volts, and the percentage will be 36.4%. So this is for the last insulator. So now what we have done, we have found out the values of the voltages V1, V2 and V3 as a percentage of voltage V. Now the second thing was the string efficiency. Again the formula is same, string voltage over total number of insulating discs into V3, which is the voltage of the disc which is closest to the conductor. So it is V over 3 into 0.364 V. So this is V3, total number of discs is 3, and string voltage is V. So string efficiency will come out to be 91.5%, and we have to multiply it with 100. So this is your string efficiency. So in this question we have found out the voltages V1, V2 and V3 as the percentage of line voltage to earth, and then we have calculated the string efficiency. Again we started by applying the KCL at node A and node B, and after that we calculated the voltages in terms of V1, and from the voltage across the string we calculated the voltages in terms of the total voltage, which is from line to neutral. Now this was the second example. For the last example of this lecture, we are going to find out voltage distribution across each unit as a percentage of the total voltage. It is same as the last one, and then again we have to find the string efficiency. So now we are not given with the value of self capacitance as well as for the shunt capacitance. So this is pin to earth capacitance is known as shunt capacitance. The only thing that is given to us is that the self capacitance is actually equals to the 5 times the pin to earth capacitance. So in this case K is equal to 5, right? And what we have to find the voltage distribution across the units as the percentage of total voltage and the string efficiency. Now what is given to us is that self capacitance is equal to 5 into shunt capacitance, right? Now if I have to find the reactance, it is actually 1 over omega C, right, for both the cases, for self reactance as well as for shunt reactance. Now if I assume that I have self capacitive reactance, it is equal to 1 ohm, right? Then for shunt capacitive reactance, the value will be 5 ohm. Why? Because the shunt capacitance is 5 times smaller than the self capacitance. So if this value is 5 times smaller, then the reactance value will be 5 times larger than the self capacitive reactance. So what I have assumed that the self capacitive reactance is 1 ohm. I have made this assumption, but then the shunt capacitive reactance, that will be 5 times larger than the self capacitive reactance. I'm not talking about the capacitance. In this case, the capacitance, the self capacitance was 5 times larger, but for the formula of the reactance, the capacitance is in denominator. So now the shunt capacitive reactance will be 5 times larger than the self capacitive reactance. So I have made an assumption that the self capacitive reactance is 1 ohm, which is this one, and then the shunt capacitive reactance will be 5 times more than the self capacitive reactance. Now this is the first assumption. The second assumption is that the voltage V1, I am assuming it is equal to 1 volt. So these are the two assumptions that I have made for the solution of this particular example. So now there are two currents, I1, capital I1 and small I1, that are moving away from node A. Now if I have to find the current I1, it will be V over XC. The voltage V, it is actually V1, and what is XC? The capacitive reactance is 1 ohm. So I1 is equal to 1 ohm, and for the current small I1, again the voltage is V1 and the capacitive reactance is 5 ohm, right? So it is 1 by 5. It is equal to, this is 1 ampere, this is the current, and this is 1 by 5, it is 0.2 ampere, right? So now what we have done, we have found out the two currents that are moving away from the node A. Now for the current that is moving towards the node A, this is for example I2. What I have to do, I have to just sum up the two currents, the capital I1 and the small I1. So the capital I2, it is equal to I1 plus capital I1, and it is 1 plus 0.2, 1.2 ampere, right? And if I have to find the voltage across this particular capacitor, it will be V2, and multiplication of I2, the current through the capacitor, and the capacitive reactance. The current through the capacitor is I2, so that is 1.2 ampere, I2 1.2 ampere, and the XC, the capacitive reactance, is 1 ohm. So the voltage V2, it will be 1.2 volt. So till this point we have found out the current I1, which is equal to 1 ampere, and we have found out also small I1, that is 0.2 ampere. Then the capital I2, this is 1.2 ampere, and from here I have calculated the voltage V2, 1.2 volt, and we assumed V1 is equal to 1 volt. Now if I have to find small I2, it will be again voltage across this particular capacitor, which is V1 plus V2, and the capacitive reactance, that is 5 ohm. Now the voltage VA, this is actually equal to this voltage VB, which is the summation of V1 and V2. So the summation of voltages V1 and V2 is in the numerator, and when we have capacitive reactance in the denominator, and the current value will be 1 plus 1.2 over 5 equal to 2.2 by 5.44 ampere. So now if I have to find again I3, it is the summation of capital I2 and small I2. So I3 is equal to small I2 plus capital I2, and it will be 1.64 ampere. So this value is 1.64 ampere, and small I2 is 0.44 ampere. Now what we have to find is this current, this is small I3, right? So now the voltage, this voltage, for example VC, this is the same voltage that is from this point till this point. So this is the summation of V1 plus V2 plus V3. So for I3 it is V1 plus V2 plus V3 divided by the capacitive reactance, which is again 5 ohm. It is equal to 1 plus 1.2 plus 1.64 over 5, and I3 is equal to 0.768 ampere. Now for the last current I4, which is from the conductor toward this node. So I4 is the summation of current I3 plus capital I3, these two currents, and it is equal to 1.64 plus 0.768. I4 is equal to 2.408 ampere. And for the voltage value V4, we have the current value I4, which is 2.408. The self capacitive reactance is 1 ohm, so V4 it is equal to 2.408 volt. So what we have done, we have started from the two basic assumptions. We assume that we have a self capacitive reactance equal to 1 ohm, and the voltage across that capacitive reactance is 1 volt, and after that we calculated the currents and voltages by using KCL and simple Ohm's law. So we have calculated all the currents and all the voltages. Now if I have to find the total voltage across the string, so total voltage across the string, it is V and the summation of all the voltages, and the value is 6.248 volt. The first part of the question was that we have to find the voltage distribution across the unit as a percentage of total voltage, right? So I will start from the top, the first disk that is closest to the tower. It will be V1 over V into 100, 1 over 6.248 into 100, and it is 16% of the total voltage, of the total string voltage. Then we have the second insulator. It will be V2 over V into 100, 1.2 over 6.248 into 100, 19.2%. Then we have the third insulator, V3 over V into 100, 6.248, and that will be 26.3%. And lastly, for the insulator closest to the conductor, it is V4 over V into 100. It is 2.408 over 6.248 into 100, 38.5%. So as we are moving towards the conductor, the voltage in terms of the total voltage across the string is increasing. So the voltage stress is increasing as we are moving away from the grounded tower and towards the conductor. This was the first portion of the question. For the second, we have to find the string efficiency, and for string efficiency the formula again is the total voltage across the string, total number of insulator discs into the voltage V4 which is closest to the conductor, 6.248 over 4 into 2.408 into 100, and the efficiency will be 64.86%. So this was the last example of the today's lecture. We have solved 3 different examples in which we have to found out the string efficiency and the voltages across all the insulators. So from the next lecture we are going to study the sag in the conductors, and we will be solving different numericals for that as well. So that's all for today. See you in the next lecture. Thank you.